Today is just challenge a little bit your conventional thinking. We've had certain things that we've been told. Like if I ask you right now, where are the lungs of the world? Where do we get all our oxygen from? A common conception is the Amazon rainforest, which is one of the things. So that's a common conception, but what we want to do today is have a look at that, and we'll have a look a little bit at what we're doing with carbon and carbon cycling. So carbon cycling is just exactly what it says. It's the cycling of carbon through all of the ecosystems. Now we're going to get a lot of graphs today, we're going to get a lot of drawings and diagrams. So I do apologize, but in order to get a better idea of what goes on behind, we need to understand a little bit about carbon cycling. And there's screens up on the side as well, for those of you who can't quite see on the front. Carbon goes around, oh my gosh, that doesn't even come out. Oh dear. It's working there, but it's not working on that. Okay, let's see if we can do it. So carbon goes around and around. I probably need Richard's pointer for this one. I can't really do this, I'm sorry, with the pointer. I'll do it with my hands. So carbon traditionally is cycled around, and we've got various things called sinks, which is where carbon goes, and we've got reservoirs where carbon stays for a while and then moves on. And it is all related to the transfer of energy and the generation of energy. And we're very fortunate in the world is that we've got this thing sitting out there, that the sun is essentially the source of all the energy that we get. And the carbon that we've got on the planet keeps going around and around. A lot of it's in rocks, a lot of it's in biomass, and a lot of it is in the ocean. And one of the things that we want to think about is a little bit on this change in the carbon that we've done in the last couple of hundred years. For hundreds of millions of years, carbon was in the bottom of the ocean and it was in the ground, and then we figured out that it was a very rich source of energy, and it makes a huge difference to society when you can get the very dense energy like gasoline, like diesel that runs this thing, like natural gas, coal. And our biggest problem that we've had so far is that we can't get that density of energy in any other form except in fossil fuels. If you think about batteries, the batteries for a Tesla weigh maybe a ton, okay? And that runs the Tesla for 350 miles. A tank of gas, to run it the same 350 miles, probably weighs 50, 60 pounds. So you've got a much higher density of energy in these fossil fuels. And what we're trying to do is we're trying to, all the time, what we're trying to do is we're trying to jam more energy into batteries, we're trying to jam more energy into our cars. I could talk about Teslas for a while and the concept that we need to be able to go 350 miles, but that's not where we're at. So have a quick look at that. You can see that we're getting quite some big emissions from volcanoes here, right? And those have got a massive effect, as we've seen from some of the talks that Richard gave. We've got massive effects from volcanoes, but we're also getting carbon coming out in other sources. But the big thing that we've done recently is we've got fossil fuels, and I hate to say it, but we've got cow farts. Cow farts are a huge source of greenhouse gases. The methane is one of the biggest sources that we've got. How does the energy get captured? Well, there's only one real way that we capture energy, apart from solar panels, which we've been able to mimic. But the only way we really capture energy is through photosynthesis. So photosynthesis is what happens in green plants, and it also happens in the brown algae that we saw floating around in the ocean yesterday. And there's some red algae as well that you'll see the photosynthesis happening. This is a chloroplast. This is where the photosynthesis happens. And everybody thinks that photosynthesis requires light entirely. It does. But there's two sides to it. There's this side which requires light. So it takes in water and gives off oxygen. And then this side over here, the Calvin cycle, doesn't actually require light. It's called the dark reaction. So it's coming in on the side. This side provides the energy right here with the light reaction. And then we have to do some trickery here in the Calvin cycle in order to get sugars. And for those nerds amongst you, this is what it looks like. This is the Calvin cycle. There will be no test on it. There's a whole bunch of energy transfer as it goes around in the Calvin cycle, and we eventually produces glucose. Just to help you understand that it's a little bit more complex than just sunlight hitting a leaf and away we go. I just managed to squeak through biochemistry at university. I just got the minimum pass, and one of the things you had to do was remember all of the phases in the Calvin cycle, and I couldn't do that. I was terrible at it, so there we go. So let's have a look at the ocean, and I apologize, this is a bit complicated. What we've really got here is we've got the atmosphere on the top, and then we've got two really different levels, or 2 or 3 different levels within the ocean. So there's the upper part, down to about 100 meters, which is where you're getting photosynthesis occurring. So light will only penetrate down to 100 meters. Most of the photosynthesis is occurring right up in the top, so this is where you're getting most of the plant activity, which is the foundation of it all. It's the same as on land. Foundation of the ocean is on the phytoplankton. The phytoplankton are then eaten by the zooplankton. The zooplankton are eaten by the, it's a little bit like that song, you know, as we go along. And what happens is all of this stuff goes on in the ocean, and it goes on in the whole ocean. It's not just little pieces. So yes, when it's colder, it goes slower. But then you're getting this movement down to the twilight zone, what they call the twilight zone. It's not the twilight zone I used to watch on TV, but it's a different twilight zone. But it's the twilight zone where squid and other things live, where the sperm whales that we saw yesterday come down. And you're getting a gradual movement of organic material from this upper area where it's generated, where there's a lot of production, and it gradually moves down into the lower levels. In the lower levels, you've got lower temperatures, you've got lower oxygen contents, and it really makes a difference as to how much breakdown you can get. Lots of recycling of carbon up here. It goes around and around and around. You go from the phytoplankton to zooplankton to the krill. The krill then get eaten by a whale shark. When a whale shark dies, it may go down, it may go up. I don't know if anybody in Cartagena saw that snake that was at the front of the ship in the water. There was a very large dead snake floating in the water. It was probably, I don't know, about from here to the pillar, long. Great big thing, great big python. And it was actually a real snake, it wasn't a fake one. And it was in the water there. Anyway, so as you think about this, the carbon that's actually stored in the oceans, remember the size of the ocean, 7/8 of the planet is covered by water, salt water. So in this case, we're looking at 1/8 is land, not all of which is covered with biomass, as we know. We've got lots of areas that have got little bits, lots of areas that don't. So the big engine, if you like, for a lot of these things is the ocean. And if we think about our fossil fuels, with the exception of coal, coal was laid down in the Carboniferous period about 300 million to 360 million years ago, when everything was wet. And what happened in the Carboniferous period was that it was very wet, it was very damp, and the trees fell down into the swamps, and they didn't decay, and over geological time, they were compressed into coal that you see today, which is why, when you look at coal, you can see leaves and fossils and all kinds of stuff still in there. So you can see fern leaves, etc. So it makes it very interesting. I grew up in a coal mining town, so that was that. My grandpa just saw coal as a way to heat water and heat his house. He wasn't really worried about, but he was an engineer, so he didn't really care about the other stuff. And then if you think about oil and natural gas were formed from microscopic plankton, zooplankton, phytoplankton that ended up on the bottom of the ocean. So over millions and millions of years, those deposits were built up. What we've done is we've dragged them out of the ground and put the carbon back up into the atmosphere. And that's where I want to have a look at where we're going. And if you can see here, there's a kind of a bit of a theme, is that we've got this very active layer here, where there's carbon is being sequestered through photosynthesis out of the atmosphere. And then there's this sink down at the bottom where it's going all the way down to the bottom of the ocean. And that's active right now. That's happening right now. How long is it going to take to replace the oil reserves? Oh, probably another 100 million years. I don't know. So, if we think about that and we go back to the terrestrial ecosystems, there's only really 6 main types of terrestrial ecosystems. There's the tundra, up in the high Arctic and down. There's actually very little tundra in the southern hemisphere. There's the boreal forest, or taiga, and again, you get some of that in South America, none in Africa, none in Australia. And that's a massive thing. I was asked, I had some friends visiting from England when I lived in northern Canada. And in England, you have things called woods, right? You have woods. So it's an area that's got a few trees. And my friend said, he was looking out at these woods, and he said, well, how big is the wood? Right? Thinking I would say, 50 hectares or 80 acres or something like that. I said, well, that particular wood goes all the way across Canada and finishes in St. John's, Newfoundland on the east coast, and I was in British Columbia. So it's about 8,000 kilometers long, and I don't know how wide. So these things are big. They're not big compared to oceans, but they're big. So they've got a fair amount of carbon in them. They're interesting. Then you've got the pretty stuff, which is the deciduous forests, which form the next belt down. So they come, again, when asked in Saskatchewan, how big is that wood? It goes all the way across Saskatchewan, Manitoba, just south of Winnipeg, and on it goes all the way across to New England. And again, interesting, because they've got lots of trees, leaves, carbon cycling goes around. The biggest thing that everybody thinks about is the tropical rainforest. The tropical rainforest is really, really strange, because these trees, they have about 50% of the biomass is above the ground, and 50% of the biomass is below the ground. So if you think about all of the kind of the fluffy bits on the top, you've got that amount of root going down underneath. So I always think it's funny when I see my neighbors and they're watering their trees. They're watering the trees right around the trunk. And they don't go out and water under the drip line, out to the drip line. So when you're watering your trees at home, remember that those roots are big and they're expansive and they're underground and there's a lot of biomass. Then obviously we have, I was just going to mention one little thing about the tropical rainforest. I did a study on the tropical rainforest when I was working in Venezuela, and we found that 90% of the biomass in the tropical rainforest is above ground. There's only a very little piece in the ground, very small roots relative to this massive thing that's growing above. And the reason for that is that the recycling of nutrients and carbon in the soil, because it's hot and wet and there's lots of microbes and bacteria, that recycling of nutrients in the soil is phenomenally quick here. There's no winter like in here, so the microbes are working 24/7 to get that nutrients recycling. So you get that very fast nutrient recycling and the exchange of energy. Obviously we have grasslands, and then the last real terrestrial ecosystem that I love to talk about is deserts. And again, those are very, very specific things, so you have to think about that. And it's interesting the way that they're distributed around the world. they tend to be distributed in patterns and lines. Tropical rainforest is this green here, but it's in the same place on the continents as it comes across, and you'll see it across through here. And you can see the influence of the way the circulation, the climate circulation patterns happen. You've got tropical rainforest, but then above it, very quickly, you've got desert. And you can see these patterns, and the patterns kind of repeat themselves. The very, very dry areas in Namibia, which if you haven't been there is a fantastic place to visit, and the very dry areas on the side of Chile here, they're in the same location on the actual continents. So as you go forward, it's kind of interesting to think about that. And then if you look quickly at aquatic ecosystems, there's really only 5 main aquatic ecosystems. There's the ocean. Then there's this transition, and I mentioned it a couple of times. If you look at the different niches, and I don't know if you noticed on the locks in the canal, on the locks in the canal, on the first 2 locks, as we came out at Colón, on the first 2 locks, up where the water was fresh, there was just a kind of a uniform slime on top of on the lock face itself. When we got down to the last lock, which is kind of an estuary because it mixes with the seawater, there was a brown area above, which is the brown seaweed, and then there was, what you can see here, and then on the lock face itself, there was a green area slightly below it, which was the green seaweed. So the green seaweeds don't tolerate exposure to air as much as the brown ones, and then you get more tolerant as you go further up the shore. But that was something that you could actually see about the lectures that I've been talking about, actually on the side of the lock. And I got to thinking about why were the first 2, why didn't they have it? Because it was fresh water. The bottom one had got barnacles on it, it had got all kinds of stuff growing on it, because it was seawater. And you'll see that everywhere. It's a fantastic thing. And then obviously you've got the marshes that we talked about, the estuaries, very, very important ecosystem. Again, these are all very, very small relative to the size of the planet. We're talking about, if you think back to the map of the globe that I showed you, the ocean, way bigger than everything else. And then the freshwater systems are lakes. Lakes are entirely landlocked, of course, and then finally the rivers as you go along. And if we think again about carbon and carbon management, if you look at this foreshore, right, it maybe extends 50 meters. It's very, very ecologically active, but it doesn't store a lot of carbon for us. If you think about the lakes are great, fabulous. Around the edge, they've got rushes and reeds and fish and everything going on, and they don't store a lot of carbon for us. So let's quickly look at ecosystems, how ecosystems work. You've got diversity, and we talked a little bit about this earlier. You've got different levels from soil to the terrestrial ecosystem. The same would happen in the aquatic ecosystems. You've got integrated and linked species that kind of all interact. So the plants grow, the snails eat the plants, something eats the snails, something that eats the snails gets eaten by something else, and we all end up back at the bottom here being decomposed once it dies off and once it comes back into the soil. So you've got this increasing complexity, landscape scale, but again, we're talking about stuff that is relatively small on the planet. And I want to explain to you now a little bit about why we need to think about where we get our oxygen from, okay? And the way an ecosystem functions. We saw that the carbon cycles. And what we've done is we've interrupted the carbon cycle by dragging a bunch of carbon that was sequestered out of the deep rocks and out of the underground and burning it. Now don't get me wrong, fossil fuels have made a huge positive effect on society. We could not have advanced anywhere near to where we are today without fossil fuels. So they're very, very important. Very, very important. But let's have a look at how an ecosystem functions. And I did a little bit of this before when we were looking at ecosystems. And what we're looking at here is how are we building up carbon in the system. So this would be a system that's been affected, in this particular case, this is a system that's been affected by a glacier. So the glacier came down here, it's wiped everything out, and then either through natural or climate change, the glacier is retreated. And the glacier retreats and it leaves a bare, open ground. And if you look at the amount of carbon that you've got in that bare, open ground, it's very, very little. As the mosses and lichens and the dandelions, for those of you who love lawns, the dandelions will always spread and they'll come out, right? The dandelions start to get a bit more biomass because you've got the top on the dandelion, and everybody knows that the dandelion root goes all the way down to Australia, at least the ones that were in my lawn did. I couldn't get them out for love nor money. And then you've got some nitrogen fixing plants like peas and alder that come in, and they come in and they start to enrich the soil. They can take nitrogen out of the air and they can fix it. And we know that we need nitrogen, phosphorus, and potassium, NPK, which is what you buy at Home Depot in a bag. It says 10, 10, 10 or 20, 15, 0. The first one is N, nitrogen, the second one is P, phosphorus, and the third one is K, potassium. As you get this naturally occurring increase, you're starting to see a build in biomass, right? So we're taking biomass, imagine this is just the same area, but over time, we're getting an increase in biomass. So we're starting to sequester carbon. This is producing oxygen. Why is it producing oxygen? Because it's taking carbon dioxide, like we saw from that nasty equation that I put up on the board, right? It's taking that carbon dioxide and it's giving out oxygen. And it keeps doing that as the biomass gets bigger and bigger and bigger in the system. So we've got big tree trunks, we've got leaves up here, and we've got lots of roots down below. And you can see that now this is a very thick, fertile soil. Again, there's more carbon gone into the soil as it goes forward, right? So as you get this secondary succession and you move things along, you can see how the soil depth increases. Now, it doesn't necessarily come up. It could break down the rocks, etc., as you go down. So from 0, where you were in a stable ecosystem before a fire or a glacier or whatever it is that affected it, then you get back to this stable, what they call climax. I never like to use the word climax because it's actually just part of a stage because it's going to eventually change. So for me, it's pseudo-climax. It's what happens to live there right now. So if you've got a lawn at home and you keep getting weeds and dandelions in, that's because it's right here. It's trying to transition itself to something else, right? It doesn't do it. But we keep cutting this back. We keep cutting this back to keep it in this particular place here when it actually wants to be over here. So you think about the biomass here. Once you get to here, there's very little change, right? You can see there, biomass increasing, carbon being sequestered, oxygen being given off. You get to here, there's no change. And if we look quickly at the terrestrial lungs of the world, we've got a little bit on tropical rainforests. And just as a thought, most of the carbon in the tropical rainforest is stored in the trunks of the trees. And it's fairly long term. It's stored, okay? It doesn't change. It's like having a full tank of gas. You want to put more gas in, you got to either use it or you've got to get a bigger gas tank. So you've got this working, and they do prevent warming because they sequester the carbon. If you were to burn all the forests and get rid of them, then they would let all the carbon out and away we'd go. And there's a few little numbers there. I mean, these are tons of carbon per hectare I actually, when I did this study, I was looking at about 400 tons of biomass, so it aligns very well with the actual carbon in the biomass. So what I want to think about now is I want to think about this flux of carbon. And this is an example in a boreal forest. And the flux of carbon in the boreal forest is a little bit different. Again, what have we seen in Canada, and what were there were some senators complaining that Canadians couldn't control their forest fires, and could they please put the forest fires out? I don't think any of the senators have actually tried to get into northern Canada. It was like, there's 3 roads that go into northern Canada in Ontario, and at the end of each one of those roads, there's a mine. Yeah, and I've worked at each of the mines at the end of one of those roads. So there's nothing up there. You can't do anything about it. It's a fire ecosystem. The boreal forest is a fire ecosystem. Even some of the trees have cones that stay closed until fire comes through. They're called serotinous cones. I mean, that's a word that we won't test you on, but these serotinous cones, as the fire comes through, they pop open. Why? Because then they release the seeds, and then the plants can grow, because the mature trees have already burned, and now you've got light, you've got water, and you've got all that kind of stuff. So you've got these serotinous cones. But if you look at this, it cycles around. It goes from burning through to an immature forest, and it's the same as what we were looking at with the glaciers. We're getting this increase in biomass. The only thing that removes biomass from the forests is if you harvest the timber. You take that timber off and you make a table. That's almost as good as making it into coal, because that table, if it's a decent one, right, is mostly wood, and it stays. So this is sequestered carbon. When we plant the forest again, it grows and it takes carbon out of the atmosphere. So it works that way. So harvesting forests is quite good. If you look a little bit, and people forget about grasslands as a carbon sink, but a carbon, like, it's an area where carbon is stored. It's a carbon store. There's a massive amount of root down below these grasslands. And if you look at this is a temperate forest that I mentioned about, similar amount of biomass above as below, a little bit more in the roots. But look at the grassland. It's got a little bit of grass on the top, and these dry grasslands have massive root systems. And if you actually take, we did a study at the University of Saskatchewan, because that's out on the prairies in Canada. We did a study, and they did an extraction of this root system for this one plant. It was about yay big. And the root system filled this massive thing like this, and it was quite incredible, because it needs to be able to get the water. So you're driven by water in this particular case. And grasslands are across the globe. So they do act as a carbon store. But again, remember, we're only talking about this part here, not the blue bit. The white bit is only 1/8 of the surface of the planet. So it really doesn't make that contribution to removing a lot of carbon from the atmosphere. And what you've got to realize is that none of the ecosystems are in a steady state. They keep changing all the time, right? A fire comes through, or there's a change in species in the ecosystem, and it flips it a little bit. When things change, you've got the opportunity to sequester carbon and change carbon. So, it's all about energy. Going back to the carbon cycle, it all comes down to the sunlight at the top, and how much goes down into the store at the bottom. And what we've got to try and do is we've got to try and think about an area. So if you think about the tropical rainforest is a phenomenal store of carbon. It's big. It's got all the broccoli-looking things that we saw. We saw it when we were in Guatemala. It was fabulous. But it doesn't change. So if it doesn't change, it can't give off oxygen as a net. It has to change. Something that's changing has the possibility of growing, sequestering biomass. So if you look at what happens in a tree, first thing you've got to remember is that all the cells in a tree respire, which means they're actively living. They're a living piece of a tree, right? Just the same as we are. At night, they continue to be using oxygen, right? There's no photosynthesis to produce oxygen at night. So you've got this massive trunk. In the tropical rainforest, you've got a little bit of root on the bottom, and you've got these massive leaves up on the top that are photosynthesizing like crazy to generate the sugars to run the tree. But it doesn't change. It actually uses up all the oxygen it gives out at night and in its roots and everything like that. So it's not changing. Where is it changing? That's where it's changing all the time. In the ocean. And Dave's educated guess before the conversation was exactly right. If we look at where we want to go for carbon sequestration, and if we think about where the carbon was sequestered before, all the oil was from the bottom of the oceans. So where we need to go and where we need to take our thinking is that where is the real source of all the oxygen? It's through the plants, of course, but it's through the plants near to the surface of the ocean. So these guys are photosynthesizing like crazy. They're tiny, or they could be the sargassum that you see. And then they get further down, and then they get into the bottom, they don't decay, and then they end up as fossil fuels. Over millennia, over actually millions of years, not thousands of years. So if we want to make a difference, we can do lots of things to reduce our use. We can change the photo to renewable energy. We can do all that kind of stuff, right? But if we really want to reduce the amount of carbon in the atmosphere and stabilize global warming, we have to think on a big scale. We have to think on a big scale that's accessible. The big scale that's accessible is what we're floating along across right now, is all of the oceans. Planting a few trees here and there, that'll offset this thing, it'll offset that thing. But when you plant, when they say they're doing these carbon offset projects on land, I calculated for the mining project, if we planted 60,000 trees a year, that we could offset our carbon footprint. But that only happens while the trees get to maturity. Once they get to maturity, it's there and it's fixed. So you have to plant another 60,000 and then another 60,000. We don't have the room or the space. We've got lots of space in the ocean. And don't get me wrong, it's not a simple solution. There are lots of things that can go wrong, that can change, that can twist in this particular case. But there are several things that have promise, and I'll look at a few of them today. And there's a few of them that are kind of a little bit out there. They probably consume more energy. And I've put a few of them up on the board right now, and we'll have a quick look at them now. But it really is, it's something that makes a difference on a massive scale. Having a carbon reduction plant in your little town that pulls out a few tons of carbon a year doesn't shift the needle. You've got 50 times the amount of carbon in the oceans as in the atmosphere, but we've got to get that out and down and out of circulation. So rather than having a carbon cycle in the thousands of years' time, we've got to think of a carbon cycle in the millions of years of time, and we've got to accelerate that deposition. And how do we do that? Well, looking at a few of these as we move forward, there's macroalgae. I mean, this is a bit hokey, but if you think about all that sargassum that we saw floating across the ocean yesterday, I think, when we came across the area, and you looked out and there was this brown stuff, and it wasn't pumice, it was actually floating seaweed. If we could drop that down to the bottom, it takes the carbon with it. and it gives us a renewable resource that we'll be able to tap in 100 million years when humans are still here. Or maybe not. Anyway, if we think about this, we can literally grow biomass on the surface. This is a bit of a very simplistic thing. We can harvest it, we can compress it, and we can squirt it down to the bottom of the ocean. It has merit. It still costs money because you need to ship and you need to compress it and you need to think about this, that, and the other. But as a seaweed thing, it can be done on a grand scale. You've got millions of square kilometers of ocean available. You can do this. There are things that need to be considered, like the changing nutrient levels at the surface, because if you're breeding all of this stuff and you're sending it down quickly, you've got to consider that. So there's changes that will occur, and you can consider it. You can also do it on a microscopic scale. If you think about it, rather than growing large plants that you can then sink, why don't you accelerate the growth of phytoplankton in an area? We do it really well in lakes. When we have eutrophication of lakes, which is by chucking in extra nutrients, we generate this algal bloom that we don't like because it's not very good for our boating. But if we could do this in the ocean, where we can get blooms of algae that can then sink, it's got merit, right? Because you can do it over thousands of square kilometers. We can get rid of large amounts of biomass, and we can do it in a way that's reasonable. And we can do other kind of smaller things. Again, sinking biomass, terrestrial biomass, into the ocean. Can we take the waste that we've got right now and put it in the ocean? The Mexican government just recently, I don't know if you've seen any of the photographs of the beaches in Cancun recently, but all that seaweed that we saw in the ocean right now is all heading to Cancun. Well, it appears to be. It's all heading to Cancun, right? So the Mexican government has decided that it's not great for the tourists. But the second thing is they've implemented a biomass program where they're collecting the seaweed and then they're mulching it onto agricultural lands. So it's actually a very good idea. It's on a very small scale. But what it does is it takes that biomass and then you put it out on the soils, and you don't need to add inorganic fertilizer, so it provides you with the nitrogen that you're going to need. And because it's seaweed, it's got a very low carbon to nitrogen. I'm getting technical, sorry. It's got a very low carbon to nitrogen ratio, which means that you don't have to add additional stuff, and it improves soil quality as well. But if we really want to make a difference, we want to sink it down onto the bottom. So we've got stuff that you can put down on the bottom of the ocean. Again, there'll be a lot of people who say, well, what about the other effects? If we don't act, then there are going to be other effects that are more serious in this part of the environment rather than in the deep oceans. So we can do this. And then there's a few what I call harebrained schemes that they want to move the deep nutrient levels up to the top. So they put these funnels in and they bring the deep nutrients up to the top to give the photosynthesis, which then they pump the stuff back down again, and there's all kinds of mechanical things. But again, these are very intensive, energy requiring, management requiring pieces. We got to think big, people. We've got to think about what we really need to do, because the oceans will continue to provide our oxygen. There's not a real concern about that. But what we want to do is to take the carbon out of the atmosphere so that we can continue burning the fossil fuels to get the lifestyle that we want. And then there's a few other things that you can do along the margins. This is along a salt marsh and mangroves. Again, the only way that we can sequester carbon in a mangrove forest is if we extend the mangrove forest out further into the ocean and we don't cut it back. And it's interesting that in the Amazon rainforest recently, over the last few years, there's been a move to do reforestation in the Amazon rainforest. So rather than grass, which was for cows, the Brazilian government has put in a program where they're doing reforestation. And there's been a change in the Amazon rainforest, whereas before it was a net consumer of oxygen, now it's a net consumer of oxygen. With this reforestation effort, where you've planted small trees, which are going to big trees, there's now a net change in the actual oxygen that's being emitted by the tropical rainforest. So it does work, and the data show it. These small programs, though, really, again, don't move the needle. There's other things like they're wanting to use carbonates and alkaline productivity. All of these have a cost and an energy cost on land. And if there's an energy cost on land, where do we get the energy from? We have to move to solar, and then we have to do all kinds of stuff like this. And then there's these schemes which, yeah, they work, but again, they move the needle very small, and we don't think in big pictures. So if you look at this, if you look at what we've got on the board here, this is a great carbon store in the roots. This is a great carbon store in the roots, a little bit, and mostly in the wood. This is a great carbon store, about 50-50 between the roots and wood. But they're stores. They're not making a change. They're not doing anything in particular, unless we do revegetation efforts, unless we plant plants. The only one that's actually giving out oxygen is this one. This is the current equivalent of the Carboniferous period, if you like. Because what happens to a marsh is that the plants grow, they fall over, and then you get this anoxic, without oxygen layer in the bottom, so therefore the plants don't decay, so you're sequestering carbon in marshes which eventually fill in and then become the soils as these trees grow over. So if we think about our oxygen source, and we think about what we can do now, the tropical rainforest is really important, not only for your mental state, knowing that there's a tropical rainforest and there's a toucan flying along it and all that kind of stuff, but it's also a store of carbon. We cut it down, we burn it, we get rid of the carbon. When we replant it, then it starts to take carbon in and give off oxygen. The largest, again, going back to the planet, the largest place that we can make a difference is in the ocean. And the reason we can make a difference in the ocean, it's a huge area and everything falls to the bottom. When it falls to the bottom, it's out of circulation, essentially. Not totally, but it's out of circulation. So therefore, any oxygen that's emitted in the surface, the carbon's captured and it goes down to the floor. So if I look at all of those schemes, including the harebrained schemes and all that kind of stuff, our best potential is to use kelp and that kind of thing, not for a bed, but for carbon sequestration as we move forward. So, the oceans have acted as a carbon sink for many years. Can we enhance them by clever, scientifically proven methods so that we can keep going with our current lifestyle? And with that, thank you very much.